Now on to the feature presentation of the evening. So there's two parts to this presentation. The first part is a bit more of a formal piece, and the second part, AJ and his lab associates will be flipping their camera around, and we'll get an inside look at their lab, and they'll be performing some testing in front of us. So I'd like to introduce Mr. AJ Schwartz, who is the Special Inspections and Materials Testing Department Head for Barry Isett Associates. Mr. Schwartz and his team work closely with clients, contractors, and engineers to confirm that building elements are installed according to approved plans and that materials meet specifications. Through detailed reports and timely communication, Mr. Schwartz's team establishes a seamless working relationship with the project team and become an integral part of the construction process. So without further ado, I'm going to turn it over to AJ. So AJ, the screen is now yours.
Jared, thanks for the intro. I'm blushing. Good evening, everyone. Welcome. I appreciate everybody being here. My name is AJ Schwartz, as Jared mentioned. I work with my team in construction and materials testing at the Lehigh Valley office of Barry Isett Associates. Like Jared said, we put together a presentation tonight, kind of touching base on all the basics of SI, and then we're going to follow that with a live tour of our materials testing lab. We thought it would be a little more fun. I don't want to rush this, but I know we are limited on time, so we'll jump right into this. The plan for tonight, first we're going to talk a little bit about the history and evolution of special inspections. We're going to talk about the code that defines special inspections, as well as the actual definition of special inspections. We talk about responsible parties during construction, and then actually the construction process involving special inspections, and then obviously touching base on some of those typical inspections. So let's start with the history. Basically, special inspections first appeared in the Uniform Building Code in 1961, and then in 1982, the House Subcommittee, they began an investigation on science and technology. And they documented a publication in 1984 titled "The Structural Failures in Public Facilities." From there, it sort of inspired BOCA, Building Officials Code Administrators, to kind of start a formal special inspections program. And then in 2000, right around the time of the IBC coming about, additional requirements were added and they were carried out through subsequent editions then, and now it's the code. And it's really required on all commercial construction projects. Basically why that SI program got started, what sort of inspired that, there was a collapse at the Skyline Plaza, 26-story reinforced concrete tower in Virginia. The cause of that was premature removal of shoring on upper floors, and then they continued to add more concrete. The result was 14 deaths and 34 injured. And the big question is, who was monitoring that concrete and certifying design strength prior to that shoring removal? And then in 1981, there was a collapse at the Harbor Bay condos. Concrete slabs were poured 8 inches thick when they were supposed to be 11 inches thick. They used plastic chairs, which were not to spec. The result of that one was 5 deaths and 16 injured. And again, who is performing ongoing inspections and documenting that steel reinforcement? Probably the biggest one in 1981, a suspended pedestrian bridge fell at a hotel in Missouri. The cause was construction changes without engineering review, and that was based off of incomplete design, a little bit of a cowboy contractor trying to do things on his own, and that resulted in 114 deaths. Was that a design flaw? Was that negligence? Was that communication? But who was making sure that construction was being conducted per up-to-date and approved construction documents? And essentially, this is where special inspections came from. Before we dive into straight into special inspectors, I also want to kind of clarify on this slide, also part of the history, but also kind of the difference between building code officials and special inspectors. Prior to 2000 and the adoption of the IBC, most municipalities performed their own inspections, but those municipalities were not familiar with specific requirements, and they did not enforce SI. Really, the building code official's job is providing public safety. They observe construction, they inspect practices. Building code officials, they check typical details of construction documents against the plans, the code and reference standards. The problem is that building code officials typically, I'm not going to say always, but lack certain certifications and expertise, such as ACI certifications, ICCs, most of the time they're not PEs or PGs. And quite frankly, it's really not their job. I'm going to just read this one because this is a good one, but the SI role is to oversee construction that requires specific knowledge and expertise exceeding the level of scrutiny the building department is responsible for, whether that's due to limitations of time or specialized expertise of critical structural elements. Essentially, the point is that special inspections is a code and it's a requirement, and it's the building official's job to enforce that code. So that code is the International Building Code. I'm going to pull a lot from this tonight as it's very specific, but I'm also going to try pull out some good things and not bore you with the details. Essentially, this is the SI Bible, and most importantly, Chapter 17. The point of inspections, the SI objective is to verify construction practices in the field and ensure they meet submittal document, code, and standard requirements. And just to clarify, this is in addition to the building officials. They have to do their job, we have to do our job. They're just different. We're not replacing them. So per IBC, special inspections is the inspection of the materials, installation, fabrication, erection, or placement of components and connections requiring special expertise to ensure compliance with approved construction documents and reference standards. I realize that was a mouthful. So simply put, it's the inspection of building elements that, if not properly installed, could cause loss of life in the event of a collapse. And also to point out is that special inspections is not for craftsmanship or finishing or means and methods. I like to look at special inspections as more of structural inspections. We're not aesthetic inspectors. Just to touch base on some of the standard inspections, it would be earthwork and soils, masonry, steel reinforcement, concrete, fireproofing, and structural steel. We're going to review some of these, and then we're also going to do some in the lab later, and also discuss a couple of outside the box additional inspections. But first, let's talk about projects that require special inspections, where application is made to the building official for construction as described in Section 105. I'm not going to tell you about Section 105, but essentially, anytime that there's an application for a permit for a commercial building, I would say 9.9 times out of 10 special inspections will be required. In the city of Philadelphia right now, L&I requires that the SI agency and the inspectors are registered with the city. The agency must be approved, and all of those inspectors have to be credentialed for inspections. This is not only for buildings, but this is also for demolition in Philadelphia. In my opinion, this is really only a matter of time before this makes its way up to local jurisdictions that they fall in line with this. Some small exceptions. It's not required for construction of minor nature or is warranted by conditions of the jurisdiction. If it's just a small project and it's in a suburb, a lot of times it can kind of fly under the radar. Not required for group U occupancies or residential, but potentially if it's an apartment building or it's a senior living home, then that would be something that would fall under the category, as well as anything with cold form light frame steel or conventional light frame. So let's talk about who pays for them. The owner or their owner's agent pays for them. Basically, the owners or the owner's representative. Basically, we just don't want any conflict of interest. However, there is a gray area. Sometimes you can have a general contractor that is a self-performer, and now they're actually an owner's rep and a contractor. But basically what ends up happening here is the point is regardless of who's paying for it, it's really the special inspector's job and the agency's job to adhere to the plans and specs and remove any conflict of interest. I just said approved agency. What is an approved agency? It is objective, competent, and independent from the contractor responsible for the work being inspected. They have the right equipment, adequate equipment to perform the required tests. The personnel, they shall employ experienced personnel educated in conducting, supervising, and evaluating. And just so everybody knows, everything that's highlighted came directly out of the IBC. So again, on the topic of conflict of interest, and I get this question often, is there any conflict of interest with the registered design professional acting as the special inspector? And the answer is no. No one has more vested interest in the building being constructed correctly than the EOR. It can be beneficial to the overall process, coordination, RFIs, certainly timely review of reports and material tests. It makes troubleshooting much easier. Communication, if we have the EOR's number and our speed dial, we can get answers on the fly. I can regurgitate this to you quick. The registered design professional in responsible charge and engineers of record in the design of the project are permitted to act as the approved agency, and their personnel are permitted to act as a special inspector for the work designed by them, provided those personnel meet the qualification requirements of this section to the satisfaction of the building official. So we did touch base on this a few slides ago, but who performs special inspections? It may only be performed by qualified personnel approved by the building official and code requirements. They're certified for the inspection tasks, ICC, ACI, whatever certification they need for that task, or like I said, the registered design professional or engineer of record. So your project needs special inspections. In a perfect world, this is the process. The design team will complete construction documents and issue for permit. By design team, I mean that could be an EOR, an RDP, registered design professional, structural engineers, it can be architects. But that permit will then trigger the need for SI. At that point, the engineer of record prepares a statement of special inspections as part of that permit set. I'll have an example of this on the next slide. And then the owner or the owner's agent engages an approved agency prior to the beginning of construction, or hopefully prior to the beginning of construction. We'll get calls sometimes with the project starting that morning. The approved agency will submit regular reports to the building official and the EOR, make sure that things are staying on track. And then at the completion of the construction, the approved agency will compile all those reports and submit a final report. That final report is then reviewed and approved by that engineer of record. And then all of that information is then submitted to the building code official or the jurisdiction. And then a certificate of occupancy will not be given without the final report being submitted. At least it should not be given. So again, this is an example of the special inspections and observations statement. This is filled out by the RDP at the beginning of the project. We use it as a basis for our proposals. It spells out exactly what inspections are required. Really, without this, the construction team is a little bit lost as to what's important to the engineer or to the building construction for that matter. And it's also important to remember that a lot of particulars regarding SI is also found in the specs, but this is for permit purposes. This is what's important. So let's get building. First of all, let me start this with inspectors are there to help. Contrary to inspector stereotype, we want things to go smooth. I'm sure we've all had issues with inspectors already, but from my standpoint, we just want things to go smooth. If there's a low break or plan discrepancies, it's a challenge for us as well. So what should your inspectors be looking at? First of all, do your homework, know your specs, know your approved plans, check out the required inspections, the statement of SI and your specs. And then there's also QA/QC inspections. Maybe an owner wants to have paving done or curbing done, something that doesn't necessarily fall under special inspection, but we'd still like to have it checked out. How often should they be involved? As often as possible is really the best answer, but at a minimum, certainly pre-construction meetings, get on track, discuss schedule, frequencies, and then certainly when construction is performed within that inspection scope. And again, I reiterated this, but project specs may dictate the duration of inspections. And scheduling is really everything. We don't want to install something and have it buried or drywalled without an inspection because it really makes more work for everyone. We don't want to miss out on concrete testing and then all of a sudden we want to put something on it, or it just doesn't work out. So the scheduling is very, very important. Um, the limits of your inspector. We have very limited authority. Sometimes I call us glorified reporters. Um, Really, the building code officials have a lot of the authority. We cannot reject things. We cannot deny things. However, we can help fix things. We can help make decisions, and we can help guide the right way to help everything work. And most importantly, we document it. I've talked with contractors, and I told them I can't tell you what you should do, but I can certainly help you do that. But I can always tell everybody what you did wrong. Nobody ever wants to see red in a report. And speaking of reports, how is that information relayed to the team? Daily field reports, material test results, all at different frequencies depending on the pre-construction meeting, and certainly immediate issues. We don't want to find out too late when something has failed. It's important to report things immediately to the construction team. We don't need any accidents. So let's talk about some of the very basic special inspections. Every new build essentially starts with soils. You want to reference geotechnical reports, civil structural drawings, and specs. Review soil types, known issues, or areas where the site that may represent construction obstacles. Are there going to be cuts? Are there going to be fills, structural or engineered fill? Laboratory analysis. We have proctors and soil classifications. Brett in our lab is going to run through with that afterwards here. Bearing requirements. We use something called a knees drop bar. We will also be showing you that. Matt will be showing you that. And then the difference between that and compaction testing. Nick will be showing us compaction testing, and that's with a nuclear density gauge. And then there's also proof rolls and backfill. We want to figure out if there's utility lines, paving, pad prep, or anything else important with the soils. And then typically the next step, we'll start digging out and we'll be putting in foundations and concrete. Footing inspections, we'll review the depth, width, again, the soil bearing, any over excavations needed, backfill or form inspections. And then there's reinforcement inspections, bar type, size, lapping, clearances, just general layout. Concrete testing, field concrete testing, we'll check batch tickets, we'll do air tests, slump, temp, cylinders. Eric, Brian, and James are going to be helping us out with that moving forward here tonight. And then there's also break schedules. It's a great thing that we discuss. Our other Eric will be taking care of discussing the other break schedules with you. But it could be 7 days, 328 days, holds, and that all gets determined at the pre-con meeting. Sometimes they may need a rush and we need a 3-day because we want to run lifts on a slab for MEP, or we want to remove shoring to get backfill in. Again, communication is everything. Pre-construction meetings, again, large pours, night work. It's definitely something to keep everybody in the know. Floor flatness, floor levelness, does that need to happen? Because that is a time-sensitive project. And then protection. This is important for the breaks. This is not only for the cylinders that we make, but this is also for slab protection or footing protection, depending on hot weather or cold weather. Masonry. We'll talk about CMU block, brick, size and alignment. We also look at reinforcing ladders, bond beams, bar reinforcing, shear walls. We'll do mortar grout placement and consistency, laboratory tests, same as compressive strength tests for concrete. Structural steel. I could probably do an entire presentation here just on bolting. Structural steel sort of in my wheelhouse, but at a minimum, member sizing and placement, bolted connections. Are they TC bolts, tension control bolts? Just snug tight. Is there a pre-tension verification needed? Which is basically where we test the bolts, make sure they're okay for use. Welding, is it just visual? Is it NDT testing that we have to bring in a CWI? Everything these days is composite decks. So we have decking and shear studs. We'll look at fasteners, spans, the studs themselves, the welds, and as well as offsite inspections. Typically, if a fabricator is AISC certified, they are not subject to that inspection. However, if that fabricator is not AISC certified, then we would have to do offsite inspections at the actual fabricating plant. We also do fireproofing. There's spray applied fire resistive materials and thin film intumescent fire resistant materials. This is one of the few inspections that needs to be ICC certified. Just a PE or PG would not be able to fit the bill to go out and do this. We look at site conditions, humidity, temperature, ventilation, weather protection. These are all things that can really hurt a construction schedule. Substrate conditions. Maybe the building's been sitting out for a year, a pandemic hit, and now all of a sudden we're going to go fireproof it. We need to make sure there's no loose scale or rust or any sort of primers or paints that would not adhere or not allow adhesion with that. Thickness measurements. With spray applied, we use that sort of elementary looking measuring device there. And then for thin film, we use a digital gauge. But this is a series of averages on sort of specific members and random locations. And then that's compared to fireproofing shop drawings. Lab density testing. Basically, we dry out a material versus we weigh it, and then we use some lead shot, and we actually do a density calculation and make sure that that is within spec. We also verify the manufacturer's recommendations are met, and then correction of deficiencies, any issues with thicknesses, or as additional trades come in and patching is required. We work actually really close with the building officials to make sure that that is all taken care of. Some additional inspections, deep foundation systems, micro piles, H piles, helical piers, high load wood diaphragms, precast concrete erection, post tension concrete, torque testing, maybe that's a racking system in a warehouse, or EFIS, exterior insulation and finish system, seismic resistance. I realize I'm throwing a lot at everyone here, but I'm also trying to save some time for the fun stuff. Additional inspections as well, stormwater BMPs, we have pipe, utility installation, rain gardens, infiltration beds, inlets, ENS controls, proof rolls, and asphalt compaction. I already discussed floor flatness, pole tests, maybe post-install anchors as well, but we do pole tests on those. NDT testing, Windsor probes, or if we have a building that we're building on, or maybe making an addition or putting a mezzanine in, we want to test the in situ concrete and make sure that that's up to strength based on the design. And as well, there's always special cases as determined by those building officials that they might want a higher level of inspection on. Do a quick review here for everybody. I know I threw a lot at you. Special inspections are required for all commercial construction projects that involve structural components. The engineer of record is permitted to act as that special inspector if adequate qualification is provided. Special inspectors are to be paid by the owner or owner's representative. The statement of special inspections prepared by engineer of record must be submitted as part of that permit application. Inspections are performed all the way through the project, and the final inspection report must be submitted prior to a project receiving a certificate of occupancy. And we've all said it, we all know it, but communication is key for a successful project. To everyone, from everyone. Scheduling is everything, and communication is everything between all parties, the EOR, the architect, the building codes and contractors, and we just sort of end up being the glue that connects them all together, and we like to work together with everyone. If anybody would like to reach out to me offline, this is my information, or if you'd just like to take me out to lunch, that would be wonderful as well. I hope that everyone found this informative. I don't know if anybody put anything in the chat or if there's any questions, but I can open that up now. All right, well, that's all right. Now, normally this would be the last slide, but this is our last slide.
Yep. Yeah, AJ, I just wanted to mention there were no questions to me as the host. So okay. hopefully we'll see some at the end.
Okay, that's fine. That works out great. Well, if you guys, we're going to stop sharing on my end now. We're going to switch this over to our iPad. If everybody could just give us a hot second while we get loaded up here, and cross your fingers for no technical difficulties.
I just kind of told him. All right, guys, can you hear us now out here in the lab?
Yes, we can hear you.
Fantastic. AJ's making his way out of the office where we were trying to do this a little quiet. And we are going to get started here.
Good. All right, everybody, I'd like to introduce Brett. We consider him our lab guru. Anytime we have a lab question, we run to Brett first. Brett is going to run you through some soil stuff here, and I'm just going to take a back seat.
All right, like AJ said, usually first thing we do is soils work with projects, and some of the first things that includes is proctors and soil classes. So basically we have a lot of that stuff set up over here for you. So we're going to run through a bit of that today here. So one of the first things we usually do here, cameraman, we usually get buckets of soil from the job site. We bring it in. First thing we're going to do is dry it out. Usually spread it on the floor, get a fan on it. Once that's done, we bring it over here. And our next step would be to take that material and sieve it over either a 3/4 inch, a 3/8, or a number 4 sieve. Now this material will sieve over a 3/4 based on the rock size. So once that's done, we basically go ahead and wet it up. So what we do is we take 12-pound samples for a 6-inch mold, and we add water to it in 100 milliliter increments to get 2% change. Once that's done, we put it in a sieve or a cylinder here, seal it off, and let that moisture kind of permeate the whole sample, make sure everything's the same moisture content, okay? Once that's done, we take it over here to our proctor machine, and as you can see, this is our proctor machine, and we have 2 different types of heads. We have circular faced, and our second face is in here, basically looks like a slice of pizza. Once that's done, we basically run this on our machine here. Though this machine can be set up for both standard and modified proctors. A modified proctor would be considered your more stringent proctor that's going to have a higher density and a lower moisture. Your standard proctors are going to be the exact opposite, a lower density at a higher moisture. And basically our geotechnical staff, when they come up with a project, they'll tell us which specs they want us to use for these projects. And sometimes the specs in the projects will tell us which test to run. I have this set up for a modified. So basically all this will do is lift this head up and lift it up. It'll reach a point here. It'll release and drop. It'll make the appropriate drop to meet ASTM 1557 or 698. And basically all that's going to happen is, John, you're going to stay on the other side of me. Up comes down. Once that's done, we take it out. Once it's filled up and lifts, we take it out, bring it over here. On the next step, we take this collar off, take a straight edge, and scrape across to get it flat. This is our volume. Now we have a set weight and a known volume. We weigh this. Once it's weighed, we dry it back. And once it's dried back, we run extra points. And when we get done, what we're basically going to be left with is an actual curve. Set that here. So as you can see, here's our proctor curve. Up at the top, we have different points of moisture. So we have 9%, 11%, 13, and 15% moisture. That correlates out to our curve. Now this curve is a function of dry density over moisture. So as you can see, as the moisture goes up, density goes up. And as the moisture continues to go up, we start to lose density. At the point where we lose density would be our maximum dry density at an optimum percentage of moisture. Now in a little bit, we're going to take this information and run it through a nuke gauge, and that is going to let us know how your compaction efforts are when you're placing fill on the job. The other thing we do as far as lab work is a soil class. And for the most part, we take sieve nests. Take sieve nests and take a known set of samples. We will sieve it through a known set of sieves. And these sieves go from 1.5 inches all the way down to a 200 micron sieve. Okay, and that'll produce a gradation. Here's our gradation, and we take it from 1.5 inches all the way down to 200, and that'll let us know our percent gravel, sand, and our fines. And then from there, we can tell you whether or not you have a silt, clay, a sand, and that'll let us know what material you guys are using. Make sure that whatever the geotech report says applies to what material we found. Now, as far as the soil class, once the gradation is done, the next step would be Atterberg limits. We would use this material over here. So basically, we have a Casa Grande cup, and this is for liquid limit. This is the point at how wet a material is just before it turns into a liquid. We also run a plasticity test, where that is how dry it is before it falls apart. Now, to do that, basically take this sample and run it through a number 40 sieve, and that'll sieve out anything that's coarse sand, gravel, and that'll leave you with your fine sand, silts, and clays. And at the end, you'll end up with something like this. A nice powder, okay? Once it's in powder form, we put it in a Ziploc bag. We add water to that Ziploc bag until we get something that forms a nice ball, okay? And then the same as a Proctor, this material sits in the bag and lets that moisture permeate the sample and gets it all the same moisture content throughout the entire sample. So what we usually do for Atterbergs is, for the plasticity limit, basically take a six gram sample and start rolling it out. And as you roll it out, you're going to get down to approximately about an 1/8 inch. And as it comes to an 1/8 inch, it just starts to break up, and you get left with little pieces of your sample. Now, at this point where it breaks up into such small little pieces, this is your plastic limit. This is the point where it's no longer plastic, it falls apart. That's your first part of the plasticity index. The second step is the liquid limit, like we talked about. Basically what you would do, hit it in the bottom, take a knife, spread it out smooth. Take a grooving tool through the deepest part of this cup. Cut a groove. Once that groove's cut, this cup is going to lift and drop at a set height to ensure that everything's following the proper ASTM. So basically all you're going to do then is start counting. At the end, you're going to end up where the groove closes in on itself. At that point, that's your liquid limit. It's no longer a solid, it's starting to become a liquid. That's going to turn into your plasticity index. Now, the reason your plasticity index is important is when you're classifying your soil, you want to find out whether or not you have a clay, a silt, a sand, and all of this is predicated on the A line. This little red dot is where the plasticity index versus the liquid limit falls on this chart. And this line here is the A line. If it's under the A line, it's usually a silt or a sand. And if it's over the A line, it's a clay. Once that's done, we put it into the chart like you've seen. And we're able to take that and make sure that we're using the proper Proctor to the proper material and provide the project with their best chances for compaction.
You good?
Awesome. The
Well done,
silts and
Brett.
clays, that's a pretty simple explanation for you guys without going too crazy. So
we go to a construction site, we get a couple buckets of sample, we have Brett run these tests, and then all of a sudden they're ready to put a pad in. So they call us and they say, hey, we need compaction testing. We got to bring this pad up 4 foot. Luckily, we have Nick Bauer here from the Mechanicsburg office. Nick has recently become our new RSO, our new company RSO. So it seemed fitting that he would handle the radiation safety officer job of using the Troxler gauge for us.
All right, so after Brett's done with all the testing, we have the proctor and everything. This is what your new gauge looks like, or they look somewhat like this. They're usually a large yellow orange shoebox, and they're decently heavy. The background behind this is there's basically a radioactive source inside the gauge at the end of this rod. This rod can then lower into the ground once you pound the pin in, and it actually emits particles into the soil. And what that does is the sensor inside this then reads whatever is going through or bouncing back into it. It also can give you the moisture content of that soil that's in place. So once you're on site, you have the pan operator, whoever's out there, they put a lift of soil down, they'll roll it in. We'll monitor that and watch it. Once they're ready for us, we'll actually step out, get the gauge. We have a base plate, a pin, and we basically go at different locations throughout that whole pad area. And we can actually pound this pin into the ground and then pull this out. And we're ready to actually test. So prior to our test, Brett would have gave us the proctor information. So we'll get that information and we actually plug that into the gauge. Once we plug it into the gauge, we do a little standard counter calibration in the field, and then we're able to run this. So once the pin's out, drop the lever down, and then you're able to run a test. We can change the amount of time the test takes. Typically, we run them for 15 seconds, a minute, 30 seconds. Sometimes it depends on the material as well. So what this actually will then read out is will actually give you your maximum dry density and your moisture based off of that proctor curve that we performed in the lab. So what that's going to give you is the percent compaction. So where do we get the percent compactions? Those are typically found in project specs, project plans. Sometimes they come from geotech reports. So we follow those. It could be anywhere from 90%, 80%, 98%, 100%. And we basically can tell that from this gauge. So this is a great tool. The other good thing that it does is if you're unsure about moisture contents within that soil, this kind of gives you a good idea. So it helps us kind of help the contractor, help our clients out in the field by saying, hey, your moisture content's way too low in the summertime. So what we're gonna have to do is wet the soil up a little bit, mix it in, recompact it, and then we'll test it again. Once we get that moisture content elevated slightly, usually we can get within that range to get the proper compaction. Vice versa, sometimes it's way too wet. So we can do things in the summertime like dry it out, let it sit, aerate it, add lime, cement stabilization, or anything like that. So that's a rundown on the new gauge.
Awesome, we're moving on. Now we have our building pad. It is now time for footing excavation. At that point, we need to figure out soil bearing and bearing capacity. Matt Flieger out of our Lehigh Valley office will be helping us out with that, showing you the drop bars I discussed in my report. Matt is actually on his way to get his own steel inspection and maybe our next certified steel inspector.
Drop bar. Nees drop bar was designed by Frank Nees in 1945. We still use it to this day. Not to be confused with compaction, this is for the bearing of the building and what strength we need out of the soil. So we excavate, we go in before we see rebar in the hole, before we pour concrete, and we run this test to determine whether or not the soil has the strength that it needs as it was designed. So we have foot increments marked on this drop bar. 1, 2, 3, and we can go into the 4th foot if necessary. We have a 25-pound weight that's lifted 3 foot all the way up and falls freely. Each foot has its own measurement. We are going to document the number of falls from the hammer in each foot. This bucket of soil would be our subgrade bottom. Bottom of excavation, bottom of footing. And we would take this. And so on. We document the number of blows with the hammer per foot. That gives us a reading that we will correlate to a chart. That's something such as this. This chart is something that we'll use in the field. And we know what type of soil we're getting into because we've checked through the geotechnical report. So if we need 3,000 bearing capacity on a clay soil, we know in the first foot, we need 5 blows per foot. The second foot, 13, third foot, 20, fourth foot, 24. If we have issues and we do not reach the strength of that soil, that's when we will remediate, we'll over excavate, and we will backfill appropriately with suitable material to achieve the strength of bearing that we need for that building. That's, I think that's about
Well done.
what we do for bearing. Anything else?
No, that's it. You know, now that we got these footings open, let's pour some concrete. Brian Kirshner here. There goes the concrete.
Yep, I think I want to be where you
Yeah,
are.
you come around. Sure. This is Brian Kirchner, also out of our Lehigh Valley office. Brian actually worked with us 2 years ago, and now he's back, and he loves it. So we just need to get rid of him, and we're happy to have him back.
All right, so first step, we're gonna start with the temperature. You test it off the chute in a wall form or your wheelbarrow. You're gonna let that set for approximately 2 minutes to get a good reading. Next step, we're gonna move into slump. 3 equal lifts of volume. More water. You need some more water in there.
Please.
We're gonna go ahead and run this 25 times. And continue. Again, 25 times. And one more time. I need the vibrator for this one. Okay, good. Then we're gonna screen it off. Press down on one side, unlock it, press down the other, come up slow. I can clear around our edges, 3 to 5 seconds. And get a measuring tape. And that would be a 3.5 inch slope. Very well.
Thank you, Brian.
Well,
Come on in. Next up is Eric Ginter, recent graduate of geology.
Yep.
He's our new shining star. We've got a lot of hope for him, and he's going to show us the air test by the pressure method.
Right, so this is our pressure method here. It's the type D air meter. This is what's most commonly used for all non-lightweight aggregates. So the first thing we'll start off here, pretty simple, similar to our pump cone. We're going to fill it in 3 litres of equal volume. First thing first, actually, you can put this on. All right, first thing first, we're going to moisten this up. All right, and then we will run it 25 times. Step. And then right here, so to get rid of any void space left with the tamping rod. Yeah, like 15 good whacks with the mallet here. And then repeat for the second one. Again, 25 rods. And then the last one. Alright, so then we'll take our strike off bar to create a nice level surface here at the top of the bucket. And make sure we clean the side of our rim here to get rid of any concrete that's on the rim. That way when we put the lid on, we don't have any air that is escaping. Nice and clean. Okay, all right. So this is our lid here. We'll seat this on and lock it into place. Now we want to take our little syringe here and pass water through one of these petcocks up here. And what this will do is to remove any excess air bubbles that are in our bucket here. One side, like, there we go. My mistake. All right, so now before we close these up, we're going to pump this up to our initial pressure line here. Give it a little tap. Wait for it to stabilize. Okay, we're good to go. We're going to close these up. Now we're gonna give it one hit and open up our main air valve here and reintroduce air into it. That's it. We can get our reading here. This is coming out to 1.6% air in this mix. And that's it. That's how you take your air reading for concrete.
So moving on, this is for normal weight concrete. On occasion, we have to deal with lightweight concrete. And if it's lightweight concrete, we have to use something called a rollometer. James Kugel, actually part of our geotech group, blesses us with his presence today. He works out of our lab often, but has also been cross-trained and has his ACI. He also drew the short straw and is doing the most difficult test of all of them. What do you think?
All right. Like AJ mentioned, the ASTM C173 is another test for air content that we use for lightweight aggregates. It has a different testing apparatus. To start off, we're going to moisten our pot. Fill our pot. 2 equal lifts by volume. For about 25 times through the steps without striking the bottom. Going to give it 10 to 15 taps with the mallet to consolidate. Our second lift, bringing us above the top. Another 25 rods, penetrating the first lift by 1 inch. Your strike off bar. Take our sponge here and clean off the rim. It's important to get the rim clean so we get a nice tight seal. Take top. Have a rubber gasket here. Make sure that's wet. Again, it's important to get a really good seal. If we get any leaks during the test will be invalid and we'll have to start this long process all over again. Okay. Next, we're going to be adding in some water and some alcohol. I'll insert our funnel. We have to put in a minimum of 1 pint of water. Our funnel here. And next we'll be adding our selected amount of alcohol. There's no defined volume of alcohol in the ASTM, but that's something that you're going to have to
that may be specified by the concrete mix or by trial and error through the project. It's important to know the volume of alcohol that you do put in, because there are associated alcohol correction factors which we'll be adding in, which we'll be using at the end of the test. And then after we've added our select amount of alcohol, we'll be filling up the rest of the tube using water. There's a glass right here on this vertical post here, which I think the numbers are on my side, but we're going to fill up that gauge to the 0 line with water. There it is. We have to get it up right to the 0 line. So for that, we'll be using a syringe to make sure we do not overfill that 0. I do not want to have to start this all over again. Now with our syringe. Excellent. Okay. The lid also has another rubber gaskets. We're going to want to wet that to make sure that we have a nice tight seal. Okay, this is the fun part. We're going to take our apparatus and we're going to be inverting it for 45 seconds for no more than 5 seconds at a time. I'll be shaking kind of like a big maraca while I do it. So hopefully I have a nice tight seal. So I'm not going to do the whole 45 seconds. I've had a long day here, but it goes something like this. We'll then take our rollometer, we'll bring it to the floor. We're going to tip it at a 45-degree angle. We're going to shake it in quarter to 1/2 turns in a shearing motion to make sure that we loosen up all that aggregate inside our pot. We're going to rotate the pot 1/3 turns to make sure that we're breaking up all that aggregate. And we'll do this for a total of 1 minute. After we've rolled for 1 minute, we'll bring it up. We're going to undo our lid. And we're going to allow our gauge here to stabilize. Once the level and the dial here has stabilized, we will, after 2 minutes, we will take that as our initial reading. We'll put the lid back on, take it back to the floor, and we would repeat our rolling motion, the same thing, 60 seconds of quarter to 1/2 turn rotations. We bring it back up to the table. We would undo our lid. We would wait another 2 minutes to allow the water level to stabilize. If the water level has not changed more than 0.25%, we can take our reading as the final reading. If it has changed more than 0.25%, put our lid back on nice and tight,
bring it back down to the floor, repeat the rolling motion for a third time. Okay? We bring it back up to the table. Undo our lid and allow the water level to stabilize once again. Now, as our repeating this, if you're repeating it for the third time, you would have taken your second reading as your new initial value. Okay, and then we'd be using this third reading to find our final value. Again, if the water level has changed no more than 0.25%, we can take that as our final reading. If it has changed more than 0.25% after our third roll, the entire test would be invalid and we'd have to repeat the whole thing all over again. If we did not add enough alcohol, it could result in excess foam. If we see more than 2% foam in our glass window here, the test would be invalid. We'd have to repeat the test all over again. So assuming that in this demonstration that that everything went right, we would have our final reading, and we would be. We're going to reuse this?
No.
Okay.
Oh, just a cylinder.
Okay. So I'm not going to dump it back in because we have put alcohol in here. But basically, we'd open up this whole testing apparatus, dump it out, make sure that there's no aggregate caught in the corners. If there was aggregate caught in the corners, then we would have to invalidate the test, start all over again. So you can see this is why this is the longest and the hardest test. A lot of ways
Not
that
want to mess it up.
there's a lot of things that can get messed up. But again, then what we would do to finally get our reading while we're doing this, we would take our final reading, we would add any calibrated cups if after our final reading, if the water level had dropped below the 9%, which is the lowest, this is the highest percentage that we could reach, we'd add water back into the funnel to get it up into view. So we would take our final reading plus add 1% for each calibrated cup. Then we would subtract our alcohol correction factor. You're going to want to check the ASTM as it has changed the past few years to make sure that you're using the proper alcohol correction factor.
Thank you, James.
Thank you.
Thank you, James. Now we're Brian up for part 2 of his presentation here. He's going to be making us a cylinder.
Real quick, this is a 4x8 cylinder. We're gonna do 2 equal lifts. I'm gonna rod this 25 times. Hold the 15 taps on each side. Good. 25 rods. Hold the 15 times. We're gonna flatten it out. Place the lid on top. And this will cure for 24 hours. So we pick it up and we'll bring it back in here. Eric, after it gets in the office.
Oh, now we made those cylinders. We brought them back from the field. We have Mr. Eric Lapos here, our project management scheduling proposal wizard.
So after the cylinders have completed their initial cure on site in a cooler overnight, they're picked up, brought back to the lab. Use a stripping tool. You have your sharp edge here, and you just that's simple. You would then take a marker, write on it your job number, date, not the date you're stripping it, but the cast date, and then the break sequence. The most common break sequence is a 7-day break, 28-day breaks, and a spare in case the 28-day breaks do not come up to strength. Kind of gives them a second chance. Very important to label them accurately. And they come over, get placed in the cure tank. They get entered into a database. The database tells us when they're broken. And then on the day they're broken, they get pulled out. We verify it's the right cylinder based on what we wrote on it. And I believe Brett is going to show us how to break a cylinder.
All right, guys, I'm back. I do the ACI compressive strength for this office. So when it's time to come break cylinders, first thing we always do is ensure the right diameter. Okay. First thing you do, about mid-height, take 2 readings, 90 degrees from each other, make sure it's 4 inches. Both readings are 4 inches. The next step is to make sure the cylinder is sitting up and down. Now, as you can see, right along the square, we're flush. Check it again, we're still flush, okay? So now we're straight up and down, we're 4 inches in diameter. Now the next step is to make sure that the top we're breaking on is flat. And to do that, take a straight edge, and this is called a feeler gauge, a little thin piece of metal. Now this is to 0.2 inches, and you just want to make sure that this can't slide under this bar, and make sure that it's flush all the way around. It's not going underneath, no matter which way I take it, okay? So now we know this thing is straight up and down, it's flat, and it's 4 inches. It's basically ready to get broken, okay? Now what we do the next is come over and choose which rings we want. We use unbonded caps. We have a set of 4 inches for these. We have a set of 6 inches. We use these to break grout prisms, and we have 2x2s for mortar cubes, okay? So what we do, set them in the rings. And when you do, you want to make sure these pad caps are flat. They're not damaged. They're still pliable. They're flat level. Everything's good. Now these have 100 uses, and we keep track of that as we go. And after 100 uses, we replace them. Basically, what we're going to do then, you want to come on over here. Set it up in the machine. You want to make sure that it's straight up and down between this lower platen and the upper platen. This platen is going to come down and compress the cylinder. So we come around, turn the machine on, make sure we're flat in, level. This is over here, allows us to retract it, hold it. We have metered advanced and full advanced. This controls your speed. Now to break 4-inch mold cylinders, we need to break between 350 and 530 pounds per second. And this is where we would adjust that. So as you go into break, you go ahead and take it to full advanced. And per the ASTM, you are allowed to run this up to 50% of its anticipated strength. So when this cylinder was molded, they used 4,000 PSI concrete. 4,000 PSI concrete needs to reach a total load of 5,000 pounds. So we would run that up to 25,000 pounds here on the screen. Your top number is your pounds, the bottom number is your speed. As soon as you hit 25, you back it down to what's called a metered advanced. And as it works, the speed here is going to start increasing. And basically, we close the door and let it break. Once it's reached its 50%, there's nothing else you can do for it. It has to just work its way through until it totally fails in the machine. Now, this machine is set up that it tells us when the cylinder has failed. That upper platen will start to move fast, and it'll recognize that the cylinder has been shot. So in the essence of time and getting you guys out of here, we're just going to run it up a little bit.
What's the force reading right now?
That's it. Now it broke. So it's peak load. This broke at 1,640 pounds. Okay. Now the next step would be to take it on a sheet of paper like this. As Eric said, our database will print out our break list. This is what it looks like. And we would write in the load and the fracture type. Now, the fracture types, without getting into a lot of detail, I have some examples for you over here. Most commonly, you'll find the type 5. This is your most common when you're breaking cylinders. This just basically shears off on a side. Your type 3, on the other hand, has these vertical cracks running through it. These are your 2 most common that we will find, okay? And then once that's done and we get the breaks done, we enter it into our Geosystems database, and every week we'll print out and send to your projects a printout of the compressive strength. Up in here is your project, your client, your contractor. This is all your important information that my colleagues basically tested through. You got slump, temp, air, and down in here is where all your compressive strengths are. So at 28 days, these broke at 5,000, 5,000, 5,000 for an average of 55,000 pounds. They would pass. So when we send that to the client, that concrete's passed. Any cylinders we have for that is then discarded.
Thank you very much, Brett. Thank you very much to everybody. That was the end of our presentation for the evening. We'd like to thank everybody for your time. That's all it takes to build a building, and that's what happens inside the SI lab. Thank you again.
Great, thanks AJ and team. That was very interesting. I guess in person we probably wouldn't have been able to fit this many people in your lab anyway. So I think it actually worked pretty well doing this virtually. We do have a few questions. You guys are still there, right?
Yeah, I'm
We're
running,
just
I'm running
Okay.
all over the place, but I'm here.
Okay. So the first question.
Now, I hope I don't have to go get Brett for this, but go ahead.
Okay, the first question is, do you use any bearing capacity gauges rather than a pounding rod?
Other than that drop bar, you mean?
Right. I'm pretty sure
assuming-
that's what it meant. Yeah.
Yeah. No, we don't. I know there's a lot of, I don't want to say controversy about what the best way is to develop soil bearing. And honestly, the truth is that drop bar, your zone of influence on a footing subgrade actually goes out more like a pyramid. However, we just haven't, outside of doing like a cone pentrometer or something like that, which is just not time effective. No, we don't. We have always used that drop bar because it's minimalistic. Every guy can have one in his truck, and it's simple. Is really the answer behind that. And hopefully, it's a project that's already had a geotechnical investigation, and we're sort of just verifying what they already know.
Okay, thank you.
Mhm.
The next question then is, at what point in the concrete testing process are decisions made to change the formulation via admixes, fiber reinforcements, etc.?
That's really all at submittal time. We don't really make, at project submittal, normally we will have that concrete mix design before we're ever even on site. So we don't make any sorts of changes out there. All we're doing is testing and verifying, really. Certainly if something isn't working and, we're repeatedly getting a low break and it's a different time of year, maybe they're going to throw an accelerator in it or something like that. But when it comes to the mix design itself, we don't do that. We're just verifying, what it was when it got there.
Great. So I do not see any questions left on here. If anybody has any questions and like them answered, please message them in the chat box, whether it's to me as the host or to the entire group. AJ, there were quite a few comments commenting on how intriguing the presentation was.
That's
So
great. We were
they-
really trying to break away from that the standard presentation that everybody's been looking at lately. And the truth is that if I was standing at a podium, there's no way I would have been able to get all of this stuff there to show it to you. So this was a great opportunity for us as well. So thank you, everyone.